What if everything you thought you knew about time was just the surface of something far stranger? We experience time as a constant, unbroken line, seconds ticking into minutes, hours slipping into days. But what if that's merely an illusion? Beneath the familiar flow of our daily lives, hidden dimensions of time might be twisting, branching, even folding back on themselves in ways that defy logic. Picture this, a universe where time isn't a single arrow but a web of possibilities, where past, present, and future exist simultaneously, waiting to be unraveled. This isn't science fiction, it's the cutting edge of physics, where the mysteries of time's hidden dimensions are pushing the boundaries of human understanding. Think about the last time you felt time slow down, maybe in a moment of sheer adrenaline, or when you were lost in something you loved. That fleeting sensation hints at something profound. Time isn't as rigid as it seems. Scientists now believe there could be layers to time we've never perceived, dimensions where clocks might tick at different rates, or where cause and effect don't follow the rules we've come to expect. Some theories suggest time could loop like a Möbius strip, with events repeating in ways we can't detect. Others propose that every decision we make splinters off into alternate timelines, creating a vast, unseen multiverse of moments. The deeper we dig, the more elusive time becomes, not a backdrop to reality, but an active, shimmering force shaping it. That's why today we're diving into 30 of the most mind-bending theories about time's hidden dimensions. From Einstein's revelations about relativity to wild modern ideas like eternalism and quantum time, we'll explore how the fabric of reality might be woven with threads of time we're only beginning to glimpse. Along the way, you'll discover how black holes could warp time into knots, why some physicists think the past might not be as fixed as we assume, and whether our entire universe is just one slice of a much larger temporal landscape. This is a journey into the unknown where every theory will challenge your perception of existence itself. So buckle up, we're about to peel back the layers of time and uncover secrets that could rewrite everything you thought was true. To grasp the idea of eternalism, imagine the universe not as a series of fleeting moments but as an unchanging sculpture where every event, your birth, the formation of stars, even the distant heat-death of everything, is already etched into its structure. This is the block universe theory, where time doesn't flow at all. Instead, past, present, and future exist simultaneously, fixed in place like frames in a film reel. Einstein's theory of relativity planted the seeds for this radical view. When he showed that time bends and stretches depending on speed and gravity, he shattered the notion of a universal now. What feels like the present to you might be the past for someone racing near light speed, or the future for an observer near a black hole. Think of it like a loaf of bread. We might experience life slice by slice, but the entire loaf, every crumb from crust to crust, exists at once. Your childhood, your next birthday, even the last breath of the last human, they're all equally real, just occupying different coordinates in space-time. This challenges something deep in our intuition. We're wired to believe the past is gone and the future isn't yet written, but eternalism suggests that's an illusion. The you reading this is just one cross-section of a larger, unchanging whole, a thread woven permanently into the cosmic fabric. Critics argue this makes life feel predetermined, but eternalism doesn't eliminate free will. It simply redefines it. Every choice you make is still yours, it's just that all possible choices already exist within the block. Like a novelist flipping to different chapters, the universe contains every version of events at once. Some physicists take this further, suggesting that if we could step outside space-time, we'd see reality as a vast, frozen tapestry, not unfolding but simply being. It's a dizzying thought. The moment you first fell in love, the dinosaurs' extinction, and civilizations yet to rise might all be equally alive in dimensions we can't perceive. Now, let's flip the script entirely. What if the present is all that truly exists? This is the heart of Presentism, a stark contrast to Eternalism. While Eternalism treats time as a frozen block, Presentism argues that only the current moment is real. The past gone, the future not yet here. There's something undeniably intuitive about this idea. After all, it matches how we experience life, each second arriving and vanishing like waves on a shore. But here's where things get thorny. If only the present is real, what does that mean for cause and effect? If the past isn't out there somewhere, how does it influence what happens now? Physics complicates the picture. Einstein's relativity showed that simultaneity is relative. Two events happening now for one observer might occur at different times for another moving at high speed. This makes defining a universal present nearly impossible. Presentism struggles to reconcile this, leading many physicists to favor Eternalism's more flexible framework. Yet some philosophers and scientists still champion Presentism, arguing that Eternalism's frozen universe feels sterile, stripping time of its dynamic, flowing nature, the very quality that makes it feel real to us. The debate isn't just academic. If Presentism is true, time travel becomes incoherent. There's no past to return to. But if Eternalism holds, the past and future are as tangible as distant stars waiting to be visited. Some interpretations of quantum mechanics even suggest that observers play a role in collapsing reality into the present, adding fuel to the fire. At its core, this clash isn't just about time, it's about the nature of existence itself. Are we fleeting flashes in a cosmic now, or timeless threads in an unchanging tapestry? The answer might reshape not just physics, but how we understand our place in the universe. Why does time march relentlessly forward, never backward? The answer might lie in something as mundane as a shattered egg. Try as you might, you'll never see those splattered yolks and cracked shells leap back into place. This everyday observation points to one of physics' most profound mysteries, the arrow of time, an invisible pointer that seems to enforce a strict one-way street for cause and effect. At its core, this arrow isn't driven by some cosmic rulebook, but by a deceptively simple concept: entropy, the universe's tendency toward disorder. Picture a sandcastle on a beach. Left untouched, wind and waves will inevitably erode its intricate towers, scattering grains haphazardly across the shore. Reversing this, sorting every grain back into perfect turrets, would require an absurd amount of energy and precision. That's entropy in action. In the 19th century, physicist Ludwig Boltzmann realized that while individual particles can move chaotically, their collective behavior follows a statistical rule. Systems naturally evolve from order to disorder. This explains why heat flows from hot to cold, why perfume disperses in a room, and yes, why broken eggs don't unbreak themselves. But here's the twist: the laws of physics themselves don't actually forbid time from running backward. At the microscopic level, particles don't care about the past or future. If you filmed two atoms colliding and played the footage in reverse, you couldn't tell the difference. So why does time's arrow point one way on the macro scale? The secret lies in the universe's starting point. The Big Bang left reality in an extraordinarily low entropy state, a rare moment of near-perfect order. Ever since, everything has been unraveling toward higher entropy, creating the illusion of time's forward flow. Some theorists suggest that if entropy could somehow decrease, time might appear to run backward for observers in that region. Imagine a bubble of reality where smoke gathers into a cigarette or spilled milk leaps back into its glass. While this isn't impossible mathematically, no such phenomenon has ever been observed. Even black holes, those cosmic entropy factories, devour order and spew out chaos. The arrow's persistence raises haunting questions. Was the Big Bang's low entropy state a fluke or a clue to deeper laws? Could alternate universes have arrows pointing in different directions? For now, the egg stays broken, the perfume stays spread, and time keeps its irreversible grip, a silent reminder that disorder might be the price we pay for existence itself. What if time itself is nothing more than a trick of the mind, a vivid hallucination stitched together by our brains to make sense of the chaos? Some of the boldest theories in modern physics suggest exactly that. In the search for a unified theory of quantum gravity, scientists studying frameworks like loop quantum gravity have stumbled upon a startling possibility. Time might not be a fundamental feature of the universe at all. Instead, it could emerge from something deeper, like how temperature arises from the jostling of countless atoms, a collective effect with no existence at the microscopic level. Picture a movie screen. What appears as smooth motion is actually a rapid-fire sequence of still images flashing by too quickly for us to notice. Reality might work the same way. At the tiniest scales, where space-time itself is thought to be granular, a seething foam of quantum fluctuations, there could be no time in the traditional sense. Physics equations at this level often don't even include a time variable, suggesting that what we perceive as the steady march of moments might be a kind of cosmic sleight of hand. This leads to an even wilder thought. Our brains could be the real architects of time. Just as a flipbook creates the illusion of movement from static pages, our consciousness might weave together discrete events into the seamless flow we experience. Studies in neuroscience support this. When you recall a memory or anticipate the future, different brain regions activate in a coordinated dance, constructing the feeling of temporal continuity. Without this biological machinery, the universe might resemble a pile of disconnected snapshots, existing all at once with no inherent order. Critics argue that denying time's fundamental role clashes with everyday experience. After all, we age, seasons change, and stars die, all processes that clearly depend on time's passage. But emergent time theories don't dismiss these phenomena, they reinterpret them. The decay of a radioactive atom or the expansion of the cosmos could reflect deeper, timeless patterns playing out in the quantum fabric. Even entropy's arrow might arise from how we're embedded in the universe, not from time itself. The implications are dizzying. If time is emergent, then concepts like before and after lose their absolute meaning. Two observers could experience sequences of events in different orders, with neither being objectively correct. Some versions of loop quantum gravity even allow for spacetime to rearrange itself, creating closed loops where cause and effect circle back endlessly. This doesn't just challenge physics, it reshapes philosophy. Free will, identity, even the nature of change itself might be stories we tell to navigate a timeless reality. Whether an illusion or not, time's grip on our minds remains unshakable. For now, we're left straddling two worlds, the one we feel and the one that might exist beyond our senses. What if you could follow a path through space-time that loops back to meet itself like a cosmic Möbius strip? General relativity allows for just that, structures called closed timelike curves, where time bends so severely that it folds back on itself. Imagine setting off on a journey and returning to your starting point, not just in space, but in time, arriving before you even left. Einstein's equations don't forbid this. In fact, certain solutions like the Gödel universe or a rotating black hole's interior suggest these loops are mathematically possible. But here's where things get messy. Step onto one of these curves and you could shake the foundations of cause and effect. Take the infamous grandfather paradox. If you travel back and prevent your grandfather from meeting your grandmother, you'd never be born. So how could you have traveled back in the first place? Physicists have wrestled with this for decades, and their solutions range from the elegant to the downright bizarre. One approach, self-consistency, argues the universe simply wouldn't let you create a contradiction. Any attempt to alter the past would somehow fold into events as they already happened. Maybe your interference was always part of history, like a time traveler who tries to stop an assassination but accidentally causes it instead. Another wild idea comes from quantum mechanics, the multiverse resolution. Every decision spawns alternate timelines, so altering the past wouldn't erase your existence. It would just create a new branch where you were never born, leaving your original timeline untouched. Then there's Hawking's chronology protection conjecture, which suggests some unseen law of physics, perhaps quantum effects, would destroy any closed time-like curve before it could form. Like a cosmic bouncer, reality might slam the door on time travel to keep causality intact. But perhaps the most radical solution is that paradoxes don't matter. Some theories propose that logic itself might operate differently inside a closed time-like curve, allowing contradictions to exist without unraveling reality. After all, if time can loop, why not the rules governing it? While no one's found concrete evidence of these curves yet, their theoretical existence forces us to confront profound questions. Is the past truly set in stone, or is it as malleable as space-time itself? The answers could redefine not just time travel, but the very nature of existence. What if the most fundamental equation of quantum gravity holds a secret that time, as we know it, doesn't really exist? That's the startling implication of the Wheeler-DeWitt equation, a mathematical framework so radical it reduces the entire universe to a single frozen moment. Formulated in the 1960s by physicists John Wheeler and Bryce DeWitt, this equation attempts to merge quantum mechanics with general relativity, but in doing so, it erases time entirely from the picture. At its core, the equation describes the universe as a static, unchanging object, like a cosmic photograph where every event, from the Big Bang to the last flicker of starlight, exists simultaneously. No past, no future, just an eternal now. To grasp how bizarre this is, think of a river. Normally, we'd describe it with equations accounting for its flow, the speed of the current, the ripple of waves. But the Wheeler-DeWitt equation is like a snapshot of that river frozen mid-motion, with no reference to how the water moves or changes. Time simply doesn't appear in the math. This isn't a mistake, it's a feature. At the Planck scale, where quantum gravity reigns, the equation suggests time might be an emergent property, a side effect of deeper, timeless processes. It's as if the universe's clockwork is an illusion, a story we tell ourselves to make sense of something far stranger. Scientists are deeply divided over what this means. Some argue the equation exposes time as a purely human construct, a convenient fiction our brains impose on a timeless reality. Others propose workarounds, like interpreting the equation's static solution as a superposition of all possible universes, a cosmic kaleidoscope where every moment could exist, even if time itself doesn't flow. Then there's the problem of time, a major puzzle in quantum gravity. If the Wheeler-DeWitt equation is correct, how do we recover the familiar, flowing time we experience? One compelling answer lies in quantum entanglement. Just as entangled particles instantly influence each other across vast distances, the universe's quantum state might encode time through relationships between events, not an external ticking clock. Imagine a deck of cards where the order isn't fixed until you shuffle and deal them. Similarly, time's arrow could emerge from how quantum states interact, creating the illusion of sequence. Critics counter that wiping time from physics leaves too much unexplained: the urgency of a ticking clock, the irreversibility of entropy. Yet the Wheeler-DeWitt equation persists, a haunting reminder that our deepest theories might be pointing toward a reality where time is nothing more than a shadow on the wall of a timeless cave. Whether it's a stepping stone to a grander theory or a dead end, one thing's certain: it forces us to question whether time is a fundamental truth or just a trick of the quantum light. The holographic principle turns our understanding of reality inside out, suggesting that the three-dimensional universe we experience, complete with the flow of time, might be nothing more than a shadow cast by information scribbled on a distant, two-dimensional surface. Imagine a movie projected onto a screen. The images appear to have depth, movement, even a sense of time unfolding, yet all that complexity boils down to flat, static frames on a reel. In the same way, this radical theory proposes that spacetime itself could be a kind of cosmic projection, with time emerging from how information interacts on that hidden, lower dimensional boundary. The idea traces back to black holes. When matter falls into one, it doesn't just vanish, it leaves an imprint on the event horizon, encoded in tiny Planck-scale pixels. Physicists realized that all the information about what's inside the black hole is somehow stored on its surface, like a hologram storing 3D data on a 2D film. Extend this logic outward, and the entire universe might work the same way. The room you're sitting in, the stars overhead, even your memories of yesterday, all could be pixels painted on the edge of reality, with time as the flicker between them. This reshapes how we think about time's arrow. If the past, present, and future are just projections, then causality might not be fundamental. Events could unfold because the underlying code demands it, not because time flows in any traditional sense. Think of a video game rendering a world in real time. The player experiences a sequence of events, but the game engine doesn't move through time. It just processes information. Similarly, in a holographic universe, time's passage might be an emergent property, a side effect of how data updates on the cosmic hard drive. Some versions of the theory go further, suggesting that our perception of time's continuity is an illusion caused by quantum entanglement, the way particles instantly influence each other across space. Just as entangled particles seem to know each other's states faster than light could travel between them, events in the hologram might be linked non-locally, stitching together the appearance of a smooth timeline from disjointed bits. If true, this could explain why time seems to flow in one direction. The hologram's code might run like a read-only file, updating in a way that creates the irreversible march of entropy we observe. The implications are staggering. If spacetime is a projection, then black holes aren't just cosmic vacuum cleaners, they're laboratories for testing the limits of information and time. Near a black hole's horizon, time slows to a crawl relative to distant observers, a phenomenon called gravitational time dilation. In the holographic view, this isn't just warped spacetime, it's a processing lag, like a computer struggling to render complex graphics. Freeze the simulation entirely, and time might stop altogether, hinting that what we call time is really just the universe computing itself into existence. Skeptics argue this reduces reality to a mathematical abstraction, stripping away the visceral experience of living in a dynamic, temporal world. But proponents counter that the holographic principle doesn't erase time, it redefines it. After all, even if time emerges from information, the illusion feels real enough to shape galaxies, civilizations, and consciousness itself. Whether an ultimate truth or a stepping stone to deeper theories, the holographic principle forces us to confront a haunting possibility. The flow of time might be the universe's most convincing mirage. Imagine a clock that never winds down, a structure that repeats its motion endlessly without batteries, without springs, without any energy at all. This isn't perpetual motion forbidden by the laws of physics, but something far stranger, a time crystal. Unlike ordinary crystals, which arrange their atoms in repeating patterns across space, time crystals repeat their structure in time, ticking through a cycle of configurations perpetually, like a cosmic drumbeat that never fades. First proposed by Nobel laureate Frank Wilczek in 2012, these exotic phases of matter defy one of physics' most sacred principles, time symmetry, the idea that the laws of the universe should look the same running forward or backward. To grasp how bizarre this is, picture a snowflake. Its intricate symmetry means it looks identical if you rotate it by 60 degrees. A time crystal takes this idea and flips it on its head. Instead of symmetry in space, it exhibits symmetry in time. In practice, this means its atoms return to their starting positions at regular intervals, like dancers in a looped routine, even without any energy input. It's as if you could nudge a pendulum once and watch it swing forever, never losing momentum to friction or gravity. The catch: time crystals don't violate thermodynamics. They don't create energy from nothing. They exist in a delicate, lowest energy state, immune to entropy's usual decay. Think of them as cosmic free riders, exploiting quantum loopholes to maintain their rhythm. In 2017, researchers brought these theoretical curiosities to life, using chains of ytterbium atoms or diamond defects to create the first experimental time crystals. Hit with a laser pulse, these systems didn't just respond. They locked into a rhythmic pattern out of sync with the pulse, like a metronome ticking at half the speed of your hand's pushes. Why does this matter? Time crystals could rewrite our understanding of equilibrium. Normal matter settles into a static state when undisturbed, like a cup of coffee cooling to room temperature. But time crystals never settle. They're restless, eternally cycling between states, offering a glimpse into a new class of quantum materials that resist thermal equilibrium entirely. Some theorists even speculate they could serve as quantum memory for futuristic computers, their stable oscillations preserving information in noisy environments. Yet the deepest implications are philosophical. If time crystals can break time symmetry, could other phenomena hide similar secrets? Might the universe harbor processes that subtly prefer a direction of time, not from entropy, but from quantum architecture? For now, these questions linger at the frontier of physics, but one thing's certain: time crystals prove that even time itself might crystallize into something we're only beginning to understand. Ever been torn between two choices and wondered what life would look like if you'd taken the other path? According to the many worlds interpretation of quantum mechanics, you did take that other path, just in a parallel universe. This mind-bending idea suggests that every decision, every quantum event, splits reality into branching timelines, each playing out its own version of events. Picture a cosmic tree with infinite branches. In one, you're watching this video. In another, you're an astronaut orbiting Mars. In yet another, dinosaurs never went extinct and humans never evolved. This isn't just speculative fiction, it's a serious theory that reshapes how we think about time's hidden dimensions. At the heart of this idea is quantum superposition, the phenomenon where particles exist in multiple states at once until observed. Schrödinger's famously morbid cat is both alive and dead in its box until you peek inside, forcing it into one state. The many worlds interpretation takes this further. Instead of collapsing possibilities into a single outcome, every possible outcome happens, each spawning a new universe. Time, then, isn't a single thread but a sprawling tapestry of alternate realities, constantly branching and diverging. Critics argue this seems wasteful. Why would the universe multiply itself endlessly just to accommodate every quantum whim? But proponents point out that it elegantly sidesteps the measurement problem of quantum mechanics. There's no mysterious collapse of the wave function. Instead, all outcomes coexist, with observers splitting into versions of themselves that experience each one. Your consciousness just happens to follow one path, unaware of the others. This also redefines time's arrow. In a multiverse, entropy might increase in every branch, but the branching itself creates a fractal flow where time isn't linear. It's a dendritic web of possibilities. Some versions of the theory even suggest these branches can reconnect. Imagine two rivers forking around an island, only to merge downstream. Similarly, quantum events could weave parallel timelines back together, creating loops or knots in the fabric of reality. This opens wild possibilities like quantum immortality, where you'd always find yourself in a branch where you survive against impossible odds. Of course, there's no way to test this. Your other selves in their own branches wouldn't be around to disagree. The implications stretch beyond physics. If every choice spawns a universe, does free will mean selecting branches, or are we just passengers in an infinite cascade of cause and effect? Artists and philosophers have wrestled with this for decades, but now scientists are too. Whether the multiverse is real or not, it forces us to confront a dizzying truth. Time might not just flow, it might fracture endlessly with every tick of the quantum clock. Einstein shattered the idea of time as a universal constant when he revealed that clocks don't tick at the same rate for everyone, a phenomenon called time dilation. The faster you move or the deeper you sink into a gravitational well, the slower time passes for you compared to someone in a different frame of reference. This isn't just theoretical, it's etched into the fabric of reality with consequences we encounter daily. Take GPS satellites orbiting 12,000 miles above Earth. Their clocks run faster than those on the ground by about 38 microseconds each day because they're farther from Earth's gravity. Without correcting for this, your navigation apps would misplace you by miles within minutes. Now, stretch this idea to its limits with the classic twin paradox. Imagine one twin blasts off on a near light-speed journey to a distant star while the other stays home. Upon returning, the traveling twin would be younger not by days but potentially by years. Time didn't just feel slower for them, it was slower, as if the universe itself pressed pause on their aging process. This isn't science fiction. Atomic clocks flown on airplanes have confirmed the effect, ticking ever so slightly out of sync with ground-based counterparts. But here's where relativity gets twisty. From the traveling twin's perspective, Earth was the one moving at near light speed, so shouldn't the stay-at-home twin be the younger one? The resolution lies in acceleration. The traveling twin changes velocity to turn around, breaking the symmetry and making their frame non-inertial. This asymmetry is the key. Time dilation isn't just about speed, it's about the path through space-time itself. Gravity warps time just as dramatically. Near a black hole's event horizon where gravity is crushing, time slows to a crawl relative to distant observers. A single hour for someone hovering near the edge could equate to decades passing elsewhere. This isn't speculative, it's baked into Einstein's equations. Even Earth's gravity creates subtle effects. Your head ages fractionally faster than your feet because it's farther from the planet's gravitational pull. These distortions reveal time not as a rigid scaffold but as a fluid, malleable dimension, bending under the weight of motion and mass. Yet for all its strangeness, time dilation isn't an illusion. It's a fundamental feature of a universe where space and time are interwoven. The faster you go, the more you trade time for space, compressing your experience of duration compared to others. This trade-off hints at a deeper truth. Time isn't just something we measure, it's something we navigate with gravity and velocity as the currents that shape our journey through it. What if the universe has a built-in failsafe against time travel chaos, a cosmic editor that tweaks events just enough to prevent paradoxes from unraveling reality? That's the heart of the Novikov self-consistency principle, a daring solution to the headaches of time travel. Proposed by Russian physicist Igor Novikov in the 1980s, this idea flips the script on paradoxes. Instead of worrying about changing the past, Novikov suggested something far simpler. The past can't be changed because the universe automatically adjusts events to stay logically consistent. Think of it like a meticulous playwright who revises every scene to ensure no plot holes emerge, no matter how much actors improvise. Take the classic example of a time traveler trying to assassinate their younger self. Under Novikov's rule, the gun would jam, the bullet would veer off course, or some other quirk of fate would intervene to keep the timeline intact. The universe wouldn't allow a contradiction, not because it's enforcing rules, but because inconsistent events simply can't happen. It's not that time travelers lack free will, it's that their actions are already woven into history's tapestry. You might set out to alter the past, only to realize you were always part of it, like an actor discovering their lines were scripted all along. This principle isn't just philosophical sleight of hand. It's grounded in physics, closed time-like curves, those hypothetical loops in spacetime that enable time travel, would naturally enforce self-consistency because the past and future are two sides of the same coin. In Novikov's view, attempting to create a paradox is like trying to divide by zero. It's mathematically nonsensical, so the universe smooths it over. Even quantum mechanics hints at this. Particles interacting with their own past selves in feedback loops must obey consistent outcomes or the equations break down. Critics argue this feels too tidy, stripping time travel of its disruptive potential. But supporters counter that it resolves paradoxes without invoking multiverses or rewriting the laws of physics. After all, we already live in a world where cause and effect seem inviolable. Novikov's principle just extends that logic to time loops, preserving the idea that every event, no matter how bizarre, must fit neatly into the causal web. Whether a cosmic safeguard or a constraint on possibility, one thing's clear. If time travel ever becomes real, the universe might have the final say on how the story unfolds. If you could step outside the universe and observe all of time at once, what would you see? The B theory of time offers a startling answer. No flow, no movement, just a vast, unchanging landscape where past, present, and future all exist equally. This stands in stark contrast to our everyday intuition, the theory of time which insists that the present is special, that time genuinely passes, and that the future is somehow not yet real. But according to B theory, the sense of time moving is nothing more than a trick of human perception, a cognitive illusion woven into the fabric of our consciousness. Think of spacetime as a book. The theory treats the story as unfolding page by page, with the reader always at a single, privileged moment, the now. But the B theory sees the entire book as already written, with every chapter from beginning to end equally real and present. You might experience life sequentially, like reading one word at a time, but the book itself doesn't change. This aligns perfectly with Einstein's relativity, where simultaneity is relative and there's no universal now. What's present for you might be past or future for someone moving at a different speed, making the theory's privileged present impossible to pin down objectively. The implications ripple through philosophy and physics. If the B theory holds, then temporal becoming the idea that events transition from future to present to past is just a psychological artifact. Your childhood isn't gone, it's simply another coordinate in spacetime, as real as the moment you're experiencing now. This challenges everything from free will to the meaning of memory. If the future is already out there, does choice even matter? B theorists argue that your decisions are still yours. They're just eternally part of the cosmic ledger, like ink dried on a page. Critics, especially theorists, counter that B theory drains time of its dynamism, reducing life to a frozen tableau. They point to the visceral feeling of time's passage, the ache of nostalgia, the thrill of anticipation, as evidence that becoming is fundamental, not illusory. Some even invoke quantum mechanics, where the collapse of the wave function seems to privilege a present moment, but B theorists fire back. Subjective experience isn't proof. After all, the Earth feels stationary even as it hurtles through space. At its core, this debate isn't just about clocks and coordinates. It's about whether the universe is a symphony unfolding note by note or a completed score where every measure already exists. The B theory doesn't just reshape time. It redefines existence itself, inviting us to wonder if the flow we cherish is just the universe's most persistent mirage. What if time isn't woven into the universe's fabric, but emerges from something far stranger, the ghostly connections between quantum particles? The emergent time hypothesis suggests just that, proposing that time isn't a fundamental ingredient of reality, but a side effect of microscopic interactions, particularly quantum entanglement. This radical idea flips our understanding on its head. Instead of time being a backdrop against which events unfold, It could be a collective hallucination conjured up by particles whispering to each other across the void. Picture a vast, silent orchestra where no conductor sets the tempo. Each musician plays independently, yet through subtle cues and shared rhythms, the illusion of synchronized music emerges. Quantum entanglement works similarly. When two particles become entangled, their states link inextricably, no matter how far apart they are. Change one, and the other responds instantly, faster than light could travel between them. Physicists suspect these entangled networks might stitch together the very fabric of time. As particles interact and entangle, their correlations could create the appearance of sequence, of cause and effect, even if no overarching time exists at the fundamental level. Recent experiments in quantum foundations lend weight to this wild notion. In lab setups, researchers have observed how entanglement entropy, a measure of quantum interconnectedness, behaves like an arrow of time, increasing as systems evolve. It's as if the more tangled particles become, the more they generate the illusion of temporal flow. Some models even suggest that spacetime itself could be a hologram projected from entangled qubits on a lower dimensional boundary, with time emerging from how those qubits update their shared information. But here's where it gets dizzying. If time emerges from entanglement, then events we perceive as happening before or after might not be universally ordered. Two observers could disagree on the sequence of events depending on how they're entangled with the system, like dancers in a routine where steps blur into simultaneity. This challenges Einstein's relativity, where temporal order is relative but still structured. In an entanglement-driven universe, time might not just bend, it could shatter into fragments, with causality becoming a local phenomenon rather than a cosmic rule. Critics argue this leaves too much unexplained. Why does time feel so continuous if it's just a patchwork of quantum handshakes? And how does entropy's relentless rise fit into the picture? Yet proponents counter that emergent time could unify quantum mechanics and gravity, two theories famously at odds. If time isn't fundamental, the conflict between quantum randomness and spacetime's smooth geometry might dissolve, revealing a deeper layer where both emerge from the same quantum substrate. Whether a profound truth or a stepping stone, the emergent time hypothesis forces us to confront a humbling possibility. The ticking clock that governs our lives might be nothing more than the universe's most elaborate shadow play, cast by particles dancing in the dark. What if spacetime isn't smooth and continuous like a sheet of fabric, but more like a finely scattered pile of sand, each grain representing a single, indivisible moment in the universe's history? This is the essence of causal set theory, a radical approach to quantum gravity where spacetime isn't a fluid continuum, but a collection of discrete events linked by cause and effect. Forget the familiar image of time as a river. Here, it's more like a sprawling family tree, with each event connected to those that came before and after in an unbroken chain of causality. At its core, causal set theory proposes that reality is built from fundamental units, tiny, indivisible atoms of spacetime that relate to one another only through their causal relationships. Think of it as a cosmic game of dominoes. Each domino represents an event, and the way they fall defines the order in which things happen. But unlike dominoes on a table, these events don't exist in a pre-existing space or time. Instead, the sequence of their falling creates time itself. The relationships between events, what causes what, are the scaffolding from which both time and space emerge. This turns conventional physics on its head. In Einstein's relativity, spacetime is a smooth, dynamic stage where matter and energy interact. But causal set theory suggests the stage itself is an illusion, a large-scale approximation of something far grainier. Imagine looking at a magazine photo up close. The smooth image dissolves into discrete dots. Similarly, if you could zoom in on spacetime past the Planck scale, you might find not a geometric continuum but a chaotic swarm of events, their order defined solely by which events influence others. One striking consequence is how it handles time's arrow. In most theories, entropy's rise explains why time flows forward, but in causal set theory, the asymmetry is baked in at the most basic level. Events can only influence future events, never the reverse, creating an inherent directionality. It's as if the universe's causal structure has a built-in one-way sign, ensuring time never backtracks. This could explain why we remember the past but not the future, not because of entropy alone, but because the fundamental architecture of reality enforces a strict causal order. Yet the theory isn't without puzzles. How does the smooth, four-dimensional spacetime we experience emerge from this disordered web of causal links? Researchers suggest it's a bit like how temperature arises from the jostling of countless molecules, a statistical effect that only makes sense at large scales. At the quantum level, the universe might be a seething froth of causally connected events, but zoom out, and it averages into the familiar flow of time and space. Critics argue that causal set theory struggles to reproduce all the features of general relativity, particularly the precise curvature of spacetime that explains gravity. But proponents counter that it naturally avoids the infinities plaguing other quantum gravity approaches, offering a fresh path to unifying physics. Whether it's the final answer or a stepping stone, one thing's certain: it forces us to reconsider time not as a stage but as a story, written one cause, one effect at a time. What does it mean for time to simply stop, not slow down, not loop back on itself, but vanish entirely from the fabric of reality? Some of cosmology's most chilling theories suggest that time itself could have an expiration date, a final tick of the cosmic clock when the universe reaches its ultimate fate. Take the heat-death scenario, where the universe expands endlessly until every star burns out, every black hole evaporates, and all matter decays into a thin, cold haze of particles drifting eternally apart. In this frozen wasteland, entropy reaches its maximum. There's no energy left to power change, no temperature differences to drive processes, just an equilibrium so perfect that nothing can ever happen again. Without change, without sequence, time loses all meaning. It's not that clocks stop, it's that the very idea of before and after dissolves into silence. But heat-death isn't the only finale on the table. Imagine instead a universe where gravity eventually overcomes expansion, pulling everything back into a singularity, the Big Crunch. Space crumples like a sheet of paper, galaxies collide, and temperatures soar to infinity. Here, time wouldn't fade, it would shatter. As the universe contracts, the arrow of time might reverse, with entropy decreasing and broken eggs reassembling themselves. But at the moment of the crunch, spacetime itself would cease to have any definable structure. There's no after, because there's no framework left to measure it. It's not an ending we can comprehend, any more than a fish can imagine life outside water. These scenarios force us to confront a paradox: if time ends, what lies beyond? Language fails us. After implies time, yet we're trying to describe a state where time no longer exists. Some physicists argue that time's end might not be absolute, that new universes could bubble into existence from the ashes, each with its own newborn arrow of time. Others propose that time's disappearance reveals its true nature, not a fundamental feature of reality, but a byproduct of cosmic activity, like the glow of a light bulb that vanishes when the power cuts out. Perhaps the most haunting question isn't how time ends, but whether its absence would even matter. If no consciousness remains to perceive the stillness, does the concept of time hold any weight? The universe might simply transition from a state of happening to a state of being, an eternal photograph where every moment that ever was is frozen in place. No past to regret, no future to fear, just silence. The end of time isn't just a physical possibility. It's a mirror held up to our deepest anxieties about meaning, memory, and the fragile flow that shapes our existence. We think of the Big Bang as the ultimate beginning, a fiery moment when time, space, and everything we know burst into existence. but what if that moment wasn't the start at all? Cyclic cosmology proposes a universe that has no true beginning or end, where time stretches infinitely in both directions. Picture a cosmic accordion, expanding and contracting over eons, with each bang merely a new chapter in an endless cycle. This isn't just poetic speculation, it's grounded in real physics. Some models suggest that before our Big Bang, there might have been a previous universe that collapsed inward, reaching a singularity before rebounding outward in a new explosion. In this view, time doesn't begin, it resets, like a phoenix rising from its own ashes. Evidence for this idea comes from quantum fluctuations, tiny ripples in the fabric of spacetime that appear even in a vacuum. These fluctuations might carry echoes of a previous cosmic cycle, like grooves on a vinyl record preserving a song from another era. When scientists analyze the cosmic microwave background, the faint afterglow of the Big Bang, they find patterns that could hint at pre-Big Bang activity. Imagine finding a fingerprint on a window pane long after the hand that left it has vanished. That's the tantalizing clue cosmologists are chasing. The math gets even wilder. Some versions of cyclic cosmology propose that universes collide in higher dimensional space, their collisions sparking new Big Bangs like flint striking steel. Others suggest that dark energy, the mysterious force accelerating our universe's expansion, could eventually reverse its role, pulling everything back together for the next cycle. Unlike the heat-death scenario where time fades into stillness, cyclic models offer a universe that renews itself eternally, a cosmic heartbeat pulsing across infinity. But how could anything survive a big crunch? Wouldn't the crushing singularity erase all traces of the past? Here's where quantum mechanics throws a lifeline. At the smallest scales, particles can tunnel through seemingly impossible barriers, and black holes might preserve information rather than destroy it. If the same principles apply to a collapsing universe, some quantum memory could bridge the gap between cycles, carrying forward the seeds of structure that shape each new cosmic dawn. Critics argue that cyclic models require fine-tuning to avoid infinite entropy buildup. Why doesn't each cycle grow more disordered? Proponents counter that the universe might find a way to reset entropy at each bounce, like a cosmic defragmentation. Others question whether we'll ever find definitive proof. After all, if time existed before the Big Bang, its traces might be locked beyond an impenetrable veil. Yet the implications are staggering. If time predates our universe, then the Big Bang wasn't creation, it was transformation. The laws of physics, the constants we consider fixed, might be heirlooms passed between cosmic generations. And if cycles continue endlessly, our universe is just one note in an infinite symphony, with time as the conductor that never lifts the baton for the final chord. What if entire centuries of human history never actually happened? The phantom time hypothesis claims exactly that, suggesting that nearly 300 years of the past, particularly the early Middle Ages, were fabricated by shadowy forces rewriting the timeline. According to this radical theory, events between the years 614 and 911 were invented, either by accident through flawed record-keeping or deliberately by conspirators seeking to legitimize their rule. Imagine opening a history book and realizing whole chapters might be elaborate fiction, with kings, wars, and cultural movements conjured from thin air to fill the gaps. The idea traces back to German historian Herbert Illig in the 1990s, who argued that discrepancies in calendar systems, architectural styles, and astronomical records point to a grand historical forgery. Take the Gregorian calendar reform of 1582. When Pope Gregory XIII adjusted the Julian calendar to correct a 10-day drift, Illig claimed the math was off. The accumulated error should have been 13 days, suggesting centuries were artificially inserted. Similarly, he noted a puzzling lack of innovation in European architecture between the 7th and 10th centuries, as if those years never unfolded. Even Charlemagne, the towering figure of medieval Europe, gets scrutinized. Could such a legendary ruler be partly mythical, his exploits exaggerated to anchor a fabricated timeline? Critics dismantle these claims point by point. Astronomers highlight that solar eclipses recorded by ancient civilizations align precisely with today's calculations, leaving no room for missing centuries. Dendrochronology, tree ring dating, shows unbroken climate records spanning the alleged phantom period, and the idea that thousands of scribes, rulers, and scholars across continents could collaborate on such a hoax strains credulity. Yet phantom time proponents counter that power structures often rewrite history to suit their needs, pointing to inconsistencies in church records or Byzantine chronicles as potential red flags. The debate exposes a deeper tension in how we reconstruct the past. History relies on fragile chains of evidence, manuscripts, artifacts, oral traditions, all vulnerable to distortion. While mainstream scholars dismiss phantom time as pseudo-history, the theory's persistence reveals an unsettling truth. The further back we peer, the fuzzier our certainty becomes. Whether a cautionary tale or conspiracy rabbit hole, it forces us to question not just what we know, but how we know it. After all, if 300 years could vanish without a trace, what else might be hiding in the shadows of time? The block universe theory paints time as an unchanging sculpture, but what if only part of that sculpture is complete? The growing block universe offers a fascinating twist on eternalism, suggesting reality isn't entirely frozen after all. In this view, the past and present exist as fixed, unshakable layers of history, stacked like pages in an ever-thickening book. But the future, that's still blank parchment, waiting to be written by the choices we make and the whims of quantum chance. It's as if the universe is a construction site where workers lay down bricks of moments behind them while scaffolding stretches ahead, its final shape undecided. This hybrid model bridges two seemingly irreconcilable intuitions. On one hand, it honors our sense that the past feels concrete. You can't undo yesterday's mistakes or relive last year's joys. Those moments are cemented into reality, their details as immutable as the fossils in ancient rock. Yet it also preserves the thrilling uncertainty of the future, the feeling that tomorrow isn't just a hidden chapter we haven't read, but one that hasn't even been typed yet. Unlike strict eternalism, where fate feels predetermined, the growing block universe leaves room for genuine spontaneity, aligning neatly with quantum mechanics' inherent unpredictability. At the quantum level, particles exist in smeared-out probabilities until measured, a property that seems to inject true randomness into the cosmos. If the future remains unformed until quantum collapses cement it into existence, then the growing block model might capture reality's true texture, solid where we've been, fluid where we're going. Philosophers love this idea because it sidesteps the free will dilemma. If the future is open, our choices aren't illusions, they're the chisels shaping each new layer of the block. Yet challenges lurk. Relativity insists that observers moving at different speeds disagree on what now means, so whose present gets added to the block. Some theorists propose privileging a universal rest frame, an invisible grid anchoring reality's growth. Others suggest the block expands unevenly, like ink diffusing through water, with each observer contributing their own thread to the tapestry. Meanwhile, quantum physicists point out that entanglement's spooky connections might require the future to be at least partially predetermined, lest causality unravel entirely. The growing block universe doesn't just reshape time, it redefines possibility itself. Every decision forks potential futures like branches on a tree, but once made, those branches harden into the trunk of history. Whether gazing at the stars or choosing a career, we're not discovering a pre-written destiny. We're architects laying bricks in a cosmos that builds itself one moment at a time. Imagine living in a world where time isn't a relentless current sweeping you forward, but a landscape you could walk through like a garden, stepping backward to revisit old paths or forward to glimpse what's ahead. This is the mind-bending premise of time as a higher dimension, a theory suggesting that what we perceive as the flow of time might actually be a spatial dimension we're biologically blind to. Think of it like the classic flatland analogy. A two-dimensional creature can't comprehend height, just as we struggle to perceive time as anything but a one-way street. But what if beings in higher dimensions experience time the way we experience space, as something they can navigate freely? For a fourth-dimensional observer, our entire timeline might lie spread out like a long roll of film. They could walk along it, stopping at any frame to examine events in what we'd call the past, present, or future. Birth, death, historical milestones, all fixed in place like cities on a map. This isn't just speculative fiction. Mathematically, treating time as a spatial dimension is perfectly valid. Einstein's relativity already fused time and space into a single continuum where gravity warps both equally. The difference is perception. We're stuck experiencing time moment by moment, like ants crawling along a rope, unaware that the rope itself has shape and structure beyond our limited perspective. Consider how a 3D object casts a 2D shadow. As the object rotates, the shadow changes in ways a flatlander couldn't predict. Similarly, a 4D being interacting with our universe might produce effects that seem miraculous or impossible to us, appearing or vanishing abruptly, altering events without cause, even remembering the future as clearly as we recall the past. Philosophers and physicists have toyed with this idea for centuries. H.G. Wells' The Time Machine imagined a traveler moving along the fourth dimension, while modern theories like string theory propose up to 11 dimensions, with time as just one thread in a vastly richer tapestry. Yet there's a haunting catch. If higher dimensional beings see time spatially, does that mean our lives are already written in some cosmic atlas? Not necessarily. Just as a 3D sculptor can mold clay into new shapes, a 4D entity might perceive time as malleable without erasing free will. Our choices could still matter. They just exist as part of a broader topography. Some interpretations even suggest that consciousness itself might be a higher dimensional phenomenon. Our minds the only part of us able to move through time, explaining déjà vu or precognitive dreams as fleeting glimpses beyond the veil. The implications ripple outward. If time is a dimension, then death might not be an end, just a location we can't return from. History wouldn't be gone. It would simply be elsewhere, preserved like a city skyline visible from a distant hill. This shifts how we think about existence, memory, even morality. After all, if the past still exists, is it truly lost? The theory doesn't just challenge our place in the universe, it redefines what place even means. Whether a profound truth or a mathematical curiosity, one thing's certain: our grip on time might be far more fragile than we ever imagined. What if the universe doesn't care which way time flows? At the quantum level, particles seem to dance to a rhythm where cause and effect can sometimes reverse, as if the future could reach back to tweak the past. This is the essence of time symmetry, the idea that the fundamental laws of physics treat past and future as interchangeable. In everyday life, we never see broken eggs reassemble themselves or coffee unstir from milk, but zoom into the realm of quantum mechanics and the rules start to blur. Experiments with entangled particles, where measuring one instantly influences its distant partner, hint that quantum events might not obey our usual notions of chronological order. Take the delayed choice quantum eraser experiment, a mind-bending setup where decisions made in the present appear to alter how particles behaved in the past. Photons fired through a detector seem to decide whether they traveled as waves or particles retroactively, based on measurements taken after they've already passed through the apparatus. It's as if the universe waits until the last possible moment to settle on a version of events, rewriting the timeline to stay consistent with what's observed. This isn't just philosophical musing, it's measurable. The equations governing these phenomena work equally well whether time runs forward or backward. suggesting that at the deepest level, the universe might not have a preferred direction for causality. Some interpretations, like the transactional quantum theory, take this even further. They propose that quantum events are mediated by waves traveling both forward and backward in time, handshakes between the past and future that solidify reality into what we observe. Picture throwing a ball and watching it fly back to your hand, not because you reversed time, but because the act of catching it was always part of the throw. In this view, every quantum interaction is a two-way street, with retrocausal echoes from the future helping shape the present. Critics argue this veers into metaphysical territory, but proponents point to tangible benefits. Retrocausality could explain quantum weirdness without invoking parallel universes or particles communicating faster than light. It might even resolve the measurement problem, why observing a quantum system forces it into a definite state. If the future influences the past, then the act of measurement isn't a collapse but a negotiation between what was and what will be. Practical implications. Imagine quantum computers leveraging retrocausality to solve problems by effectively guessing answers before they're calculated. Or consider closed timelike curves, where time loops could exploit this symmetry to send information or even particles backward without paradox. The catch: these ideas remain fiercely debated, with no consensus yet on whether time symmetry is a quirk of math or a genuine feature of reality. One thing's certain: if time truly works both ways at the quantum level, it forces us to rethink the very nature of existence. Maybe the past isn't set in stone, maybe the future isn't unwritten, or maybe, just maybe, time is less an arrow and more a mirror reflecting possibilities in both directions, with our perception of flow just an illusion in the glass. We often assume time flows at a constant rate, yet why does a minute spent waiting for a late bus feel endless, while an hour laughing with friends vanishes in a blink? The answer lies not in the universe's clockwork, but in the quirks of our own biology. Neuroscience reveals that our perception of time isn't a passive reflection of reality. It's an active construction, a fragile illusion woven by the brain from scattered sensory threads. At the heart of this illusion is the specious present, a term coined by psychologist William James to describe how we experience not just instantaneous moments, but a stretched-out window of time, typically 2 to 3 seconds long, where past, present, and future blur into a seamless whole. Think of listening to a melody. You don't hear individual notes in isolation. Your brain stitches them together into a flowing tune, creating the impression of continuity. This temporal glue relies on specialized neural circuits, particularly the basal ganglia and prefrontal cortex, which act as the brain's timekeepers. When these regions are disrupted by drugs, neurological conditions, or even extreme stress, time perception warps dramatically. For someone with Parkinson's disease, where the basal ganglia degenerate, seconds might crawl like hours. Meanwhile, adrenaline floods during a car crash can make events unfold in eerie slow motion, as the brain crams extra sensory detail into memory, creating a false sense of prolonged time. But here's the twist: the brain doesn't just measure time, it predicts it. Our neural networks are constantly running ahead of reality, anticipating what comes next based on past experience. This predictive machinery explains why routine tasks, brushing your teeth, commuting to work, seem to compress in retrospect. Your brain filters out predictable input, creating a temporal shorthand that makes familiar events feel fleeting. Novelty, by contrast, stretches perceived time because the brain must work harder to process unexpected stimuli. Vacation days packed with new sights and sounds feel longer in memory than months of routine, not because the clock changes, but because your consciousness records more rich, unruly data. The interplay between attention and time reveals another layer of the illusion. When you focus intensely, say, watching a pot boil, your brain's internal timer becomes hyper-aware of each passing second, magnifying duration. But distract yourself and time seems to accelerate as cognitive resources are diverted away from tracking it. This explains why childhood summers feel endless while adulthood blurs by. As we age, fewer experiences are genuinely novel, so the brain stops cataloging them in detail, creating a telescoping effect where years shrink in hindsight. Even more unsettling, experiments show that our sense of time can be hacked. In one study, participants who viewed images of fearful faces perceived them as lasting longer than neutral expressions, proof that emotion literally stretches time in the mind. Other research reveals that body temperature alters time perception. Feverish patients overestimate durations while cooled subjects underestimate them. These findings suggest time isn't just a mental construct, it's a bodily one, intertwined with physiology in ways we're only beginning to map. What does this mean for time's fundamental nature? If consciousness can bend and warp our experience of duration, could time itself be a byproduct of observation? Some quantum interpretations flirt with this idea, proposing that reality only solidifies when measured, implying time might not flow without a mind to perceive it. Though controversial, this view aligns with the eerie fact that no physical law explains why we remember the past but not the future, perhaps memory, and thus time's arrow isn't written into the cosmos but etched by the peculiar way our brains filter reality. Whether neural artifact or cosmic truth, one thing's clear: the ticking clock in your head is a storyteller, not a stenographer. It stitches together fragments of sensation, emotion, and memory into the narrative we call now, a fleeting collage that feels like time, but is really just the brain's best guess at how to keep us anchored in the storm of existence. What if time doesn't flow smoothly like a river, but clicks forward in tiny, invisible steps like the frames of a film, reel too fast for our eyes to detect? This is the essence of the chronon hypothesis, a radical idea proposing that time isn't continuous but quantized, broken into indivisible fragments called chronons. Just as matter is made of atoms and light comes in photons, time itself might be pixelated, with each chronon representing the smallest possible unit of temporal change. Think of it like the refresh rate on a screen. Reality might update itself in discrete ticks, too rapid for us to notice, but fundamental to the universe's inner workings. The concept traces back to the notion of Planck time, the smallest meaningful interval in physics, roughly 10 to the power of -43 seconds. At this scale, the smooth fabric of spacetime predicted by general relativity dissolves into a seething quantum foam where time and space lose their classical meaning. If chronons exist, they'd likely hover around this unimaginably brief duration, acting as the universe's ultimate timekeeping mechanism. Unlike ordinary seconds, which we can divide infinitely in theory, a chronon would be the end of the line, a temporal atom that can't be split further. Testing this idea isn't as far-fetched as it seems. Some experimental setups in quantum optics already push the limits of time resolution. Ultra-fast lasers firing pulses lasting a toscan's billionth of a billionth of a second could one day stumble upon evidence of time's granularity. If chronons exist, these lasers might reveal gaps in time's structure, moments where nothing changes because the universe hasn't refreshed to the next tick. It's like filming a hummingbird's wings with a slow-frame camera. If your shutter isn't fast enough, the motion appears blurred, but with sufficient precision, you'd catch the instance where the wings are frozen between beats. The implications ripple through physics. If time is quantized, our understanding of causality might need an overhaul. Events wouldn't transition seamlessly from cause to effect. They'd jump between chronons like a stop-motion animation, raising questions about what happens in the gaps. Could information slip through these cracks? Could particles briefly exist outside time altogether? Some models suggest that chronons might explain quantum superposition, the way particles seem to occupy multiple states until measured. If time itself stutters, particles might not need to choose a state until the next chronon ticks over. Critics argue that quantized time conflicts with relativity, where smooth, continuous spacetime is central. Yet proponents counter that at the quantum scale, even space might be granular, as hinted by loop quantum gravity. If both space and time are pixelated, the universe could be more like a cosmic computer rendering reality frame by frame than a fluid continuum. Whether a profound truth or a stepping stone to deeper theories, the chronon hypothesis forces us to confront a startling possibility. The eternal flow we call time might be the universe's most convincing illusion. What if time isn't just one dimension but two, like a clock with not only an hour hand but a second, independent minute hand ticking alongside it? This is the radical premise of two-time physics, a theory proposing that our universe might hide an extra-temporal dimension, invisible to our senses but fundamental to the fabric of reality. At first glance, the idea seems absurd. We're used to thinking of time as a single, unbroken thread stretching from past to future. But just as adding spatial dimensions beyond the three we perceive unlocks new possibilities, like folding paper through higher dimensions to bridge distant points, an extra time dimension could solve some of physics' deepest puzzles, particularly the stubborn divide between quantum mechanics and gravity. Picture a sheet of music. Normally, you read it left to right with time flowing in one direction. Now imagine a second timeline running vertically, creating a grid where notes intersect in ways that wouldn't make sense on a single line. In two-time physics, events could have coordinates not just in space and one time dimension, but in two temporal axes. This might explain why quantum particles behave so bizarrely when we try to pin them down. Their weirdness, existing in multiple states at once or teleporting information instantly, could be shadows of interactions playing out in higher temporal dimensions we can't directly observe. The math behind this is less speculative than it sounds. String theory, one of the leading frameworks for quantum gravity, already requires extra spatial dimensions to work, usually 6 or 7, curled up too small to detect. Two-time physics simply extends this logic to time itself. Some versions of the theory propose that while we experience time as linear, the second time dimension is compactified, like a tiny loop at every point in spacetime. This hidden structure could act as a kind of cosmic tuning fork, resonating in ways that stabilize the universe's fundamental constants. Others suggest the second time dimension isn't hidden but orthogonal, intersecting our familiar timeline at right angles. In this view, causality might branch like a tree, with events influencing each other across both temporal axes in ways that appear paradoxical when flattened into a single dimension. One compelling application of two-time physics is its potential to unify relativity and quantum mechanics. Einstein's gravity describes spacetime as a smooth, curving landscape, while quantum theory portrays particles as probabilistic waves collapsing upon observation. The clash between these pictures, one continuous, one discrete, has stumped physicists for decades. But with an extra time dimension, quantum weirdness could arise from our limited perspective, like flatlanders trying to comprehend shadows cast by a rotating 3D object. Entanglement's spooky action at a distance might just be particles communicating through higher temporal pathways we can't see. Even black holes' singularities could resolve into elegant structures when viewed through the lens of multiple times. Skeptics raise valid concerns. Wouldn't a second time dimension allow for closed time loops on microscopic scales, permitting paradoxes where effects precede causes? Proponents counter that the extra dimension might be constrained by unseen symmetries, preventing chaos while still enriching physics' toolkit. Others note that while two-time theories are mathematically elegant, they're notoriously hard to test. If the additional time dimension is compactified at the Planck scale, current technology couldn't probe it directly. Those subtle signatures might lurk in high-energy particle collisions or cosmic ray data. Whether a profound truth or a mathematical curiosity, two-time physics forces us to confront a humbling possibility. our grasp of time might be as limited as a caterpillar's understanding of flight. Just as adding a third spatial dimension transforms a circle into a sphere, an extra time dimension could reveal that what we call the universe is just a slice of something far richer, a reality where clocks don't just tick but dance. What if every moment of your life, every joy, every heartbreak, every ordinary Tuesday is destined to replay again and again, infinitely? This is the haunting premise of the time loop universe, where existence isn't a linear march but an endless cycle, like a cosmic record stuck on repeat. Philosopher Friedrich Nietzsche called it eternal return, the idea that the universe repeats itself identically in infinite iterations. Imagine living your life over, not just similarly, but exactly the same choices, the same mistakes, the same outcomes, with no memory of the previous cycles. Nietzsche posed this as the ultimate test of meaning. If you knew your life would recur eternally, would you despair or embrace it as divine? Modern cosmology breathes eerie new life into this ancient idea. Certain solutions to Einstein's equations suggest a universe that could collapse and rebound endlessly, each cycle a near-perfect replica of the last. Unlike the Big Bang and Crunch models where each rebirth reshuffles reality, a true time loop universe would replay like a film reel burned onto the fabric of existence. The math allows for it. If entropy resets perfectly at each bounce, a gargantuan. If the universe might reconfigure itself identically, atom for atom, thought for thought. You'd blink awake one day, unaware this is the trillionth time you've lived this life, or the first. Yet even slight variations in cycling universes open wild possibilities. Conformal cyclic cosmology, proposed by Nobel laureate Roger Penrose, suggests that while particles and structures dissolve at the universe's end, their imprints encoded in spacetime's geometry echo into the next cycle. The cosmic microwave background might bear faint fingerprints of a previous eon's black holes, like shadows on a cave wall. Here, time loops aren't perfect copies but evolving patterns, where each iteration inherits ghostly traces of its predecessors. The implications unsettle our deepest intuitions. If time loops, is free will an illusion, or do we choose anew each cycle? Could déjà vu be fleeting memories of prior loops, or just cosmic déjà intendu, the universe whispering its recursive design? Whether a poetic metaphor or physical truth, the time loop universe forces us to confront a chilling question. If all this has happened before, what makes now matter? Perhaps the answer lies not in the cycle's repetition, but in how we dance to its rhythm, knowing the music never truly ends. The world around us thrums with motion, leaves trembling in the wind, planets tracing their orbits, heartbeats counting out the rhythm of life. But what if none of it is real? Static time theory dares to suggest that change itself is the grand illusion, a trick played on our senses by a universe that's actually frozen in eternal, unmoving instant. Imagine the cosmos as a colossal sculpture, every event from the Big Bang to the heat death of stars fixed in place like stars embalmed in glass. What we call time isn't a river flowing, but a spotlight moving across this sculpture, giving us the false impression of sequence and causality. This idea isn't just philosophical speculation, it's rooted in the cold, hard math of physics. Einstein's equations treat spacetime as a single, four-dimensional block where all moments coexist. Just as a DVD contains every scene of a movie simultaneously, the universe might hold every moment in existence at once, with our consciousness acting like the laser reading the disk, perceiving one frame at a time. Even quantum mechanics hints at this stasis. When particles exist in superposition, multiple states at once until observed, it's as if they're frozen in potentiality, waiting for our attention to play their story. Static time flips everyday logic on its head. Think of a movie reel. The hero's birth, triumphs, and death are all present on the film from the start, yet viewers experience them linearly. Similarly, your childhood and your distant future might already be out there, written into the fabric of reality while your brain stitches them into a narrative of progress. This raises haunting questions about free will. If the future is as unchangeable as the past, are our choices just mirages? Proponents argue that freedom lies in the illusion itself. Like an actor improvising lines that were always scripted, we live authentically within the constraints of the block. Skeptics point to entropy as proof of time's dynamism. How can the universe be static if disorder always increases? But static time theorists counter that entropy's arrow is just another coordinate in the block, a gradient painted onto the sculpture. The egg that cracks today and the whole egg yesterday are both equally real. We're just traversing the gradient in one direction. Even memory fits this model. Recalling the past isn't retrieving data from some vanished era. It's accessing another part of the static structure, like flipping to an earlier page in a book that already contains every page. The theory's boldest claim, that motion itself is impossible. When you watch a ball fly through the air, static time suggests it's not moving at all. Instead, the universe contains an infinite series of ball positions, stacked like slices in a loaf of bread, and your consciousness leaps from one to the next, creating the illusion of trajectory. This mirrors how early film projection tricked audiences into seeing fluid motion from still images. If true, then every sunrise, every falling tear, every explosion in the cosmos is just a frozen tableau, with our minds supplying the phantom sense of flow. Critics argue this reduces life to a lifeless diorama, stripping the universe of its vibrancy. But static time doesn't deny the richness of experience, it recontextualizes it. Joy and sorrow aren't less real because they're eternal, they're more so, etched permanently into the cosmos. Whether a profound truth or a mathematical abstraction, the theory forces us to confront a staggering possibility. The ceaseless change we cherish might be the universe's most convincing magic trick, a stillness so perfect it dazzles us into seeing motion where there is none. Picture throwing a ball and watching it arc through the air, only instead of the ball obeying the usual laws of motion. It behaves as if your future catch somehow guided its flight from your hand. This isn't just a playground fantasy, it's the essence of the transactional interpretation of quantum mechanics, where particles send waves not just forward through time, but backward, creating a bizarre kind of cosmic negotiation between past and future. At the heart of this theory lies a radical idea. Quantum events aren't determined solely by causes in the past, but through handshakes between waves traveling in both temporal directions. The roots of this idea stretch back to the puzzles of quantum measurement, when a particle like an electron exists in superposition, being both here and there until observed, what finally pins it down to one location. Traditional interpretations invoke wave function collapse, a sudden and unexplained transition from possibility to reality. The transactional interpretation offers an elegant alternative. Here, every quantum event is mediated by two waves, an offer wave moving forward in time and a confirmation wave traveling backward. When these waves match up, like a key fitting a lock, they form what physicists call a handshake, solidifying the particle's behavior into what we observe. Imagine shouting into a canyon and hearing your echo return at just the right moment to reinforce your voice. That resonant feedback is how particles choose their states through echoes from the future. This time-symmetric view resolves some of quantum mechanics' strangest paradoxes. Take the delayed choice experiment, where a photon seems to decide whether it traveled as a particle or wave retroactively, based on measurements made after it's already passed through the apparatus. In the transactional framework, this isn't a paradox, it's the confirmation wave from the future shaping the photon's past behavior, ensuring consistency. Even entanglement's spooky action at a distance becomes less mysterious. Paired particles might instantaneously coordinate because their transactional handshakes span time non-locally, like pen pals exchanging letters that somehow cross in the mail. Critics argue that accepting waves from the future reeks of teleology, the idea that events are influenced by their ultimate purpose, but proponents counter that the math is rigorously causal with no true effect before cause. The confirmation waves aren't conscious choices, they're mathematical solutions to boundary conditions, no more mystical than ripples in a pond rebounding off the shore. Some versions of the theory even sidestep the need for wave-function collapse entirely, suggesting that the apparent randomness of quantum outcomes emerges from incomplete knowledge of these two-way transactions. A die roll only seems unpredictable because we can't see how future constraints shaped its fall. The implications ripple beyond quantum puzzles. If the transactional interpretation holds, it could redefine how we think about time's arrow. Entropy's rise might not be the sole source of time's direction. Instead, the asymmetry could arise from how offer and confirmation waves statistically favor certain handshakes over others. It also breathes new life into John Wheeler's participatory universe, the notion that observers play a role in shaping reality. Here, observation isn't passive witnessing but an active transaction, with the future subtly sculpting the past to meet its demands. Whether a profound truth or a clever mathematical fiction, the transactional interpretation forces us to confront a startling possibility. The universe might not just remember the past, it could be taking orders from the future. A man strolls through a familiar London alley, turns a corner, and suddenly finds himself surrounded by horse-drawn carriages and gas lamps, only to blink and have the modern city snap back into place moments later. A woman driving through rural Vermont swears she passed through an invisible barrier where the landscape shifted to autumn colors in mid-July before reverting just as abruptly. These aren't scenes from a sci-fi novel. They're real-life accounts of the time-slip phenomenon, where people report brief, involuntary jumps into what appears to be another era, often with vivid sensory detail before snapping back to their original moment with no explanation. Unlike déjà vu, which feels like a glitch in memory, time slips immerse witnesses in fully realized environments that match historical periods down to forgotten smells, clothing textures, and even dialects no longer in use. What could trigger such bizarre experiences? One compelling angle ties these episodes to spacetime itself behaving like a frayed fabric, where microscopic tears or quantum fluctuations momentarily expose hidden layers of reality. At the quantum scale, particles routinely pop in and out of existence due to vacuum fluctuations, tiny energy bursts that momentarily bend the rules of classical physics. If spacetime shares this granular, frothy nature, as theories like loop quantum gravity suggest, then rare macro-scale fluctuations might create temporary, thin spots where different eras bleed together. Think of it like a scratched DVD skipping between scenes, except the disk is the fabric of reality, and the scratches are natural spacetime defects we don't yet understand. The role of human perception adds another layer of intrigue. Neurologists note that time-slip accounts often cluster around locations saturated with emotional or historical significance, ancient battlefields, Victorian-era buildings, or sites of profound personal memory. This raises the possibility that intense psychological states, heightened awareness, grief, or even mundane stress could temporarily tune the brain like a radio receiver, picking up residual imprints of past events. Some theories propose these imprints might be stored in the environment itself, akin to stone tape theory, where materials like limestone or iron-rich rock record energetic traces of trauma or celebration that certain individuals unconsciously play back. Yet skeptics offer more grounded explanations. Temporal lobe epilepsy can trigger hyper-vivid hallucinations of alternate realities, while dissociative states might fracture someone's sense of temporal continuity, creating the illusion of time travel. Even mundane environmental factors like infrasound from old pipes or geomagnetic anomalies could induce disorientation that the brain interprets as a chronological shift. The brain is a relentless pattern seeker, quick to stitch chaos into narratives, especially when confronted with the uncanny. But the most tantalizing hypothesis bridges neuroscience and quantum physics. Or theory, proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, suggests consciousness arises from quantum vibrations in microtubules within brain cells. If correct, these quantum processes might occasionally entangle with the fabric of spacetime itself, briefly aligning a person's perception with non-local or past events. Imagine dipping a thread into a river. Normally it flows with the current, but if the thread momentarily snags on a submerged rock, it could jerk backward against the stream. In this metaphor, the thread is consciousness, the river is time's arrow, and the rock is a quantum fluctuation in the universe's deepest code. Whether neurological quirks, spacetime glitches, or something beyond current physics, time slips challenge our assumptions about reality's rigidity. They hint that the past might not be gone, just stacked beneath the surface, waiting for the right conditions to flicker through. Until science unlocks these mysteries, these fleeting windows into other moments remain both a puzzle and a promise that time may not be the prison we think it is. Time feels like a straight path, an unbroken line from past to future. But what if it's more like a sprawling network of interconnected highways with twists, branches, and even loops we can't perceive? The idea that time might have more than one dimension isn't just science fiction. It's a serious mathematical possibility that could rewrite our understanding of causality itself. Imagine living on a sheet of paper, unaware of the third dimension above you. Now apply that to time. We experience it as a single arrow, but hidden beneath the surface, there could be entire temporal landscapes we've never dreamed of. The math behind this is surprisingly elegant. Just as adding spatial dimensions transforms a point into a line into a plane, and a plane into a cube, adding a second time dimension would reshape causality into something far richer and stranger. In a two-time universe, events wouldn't just have coordinates in space and one time dimension. They'd exist in a four-dimensional block where before and after could branch like a tree. Picture a chessboard where pieces move not just forward and backward but also sideways through time, their paths weaving in ways that defy linear logic. Some theoretical models, like F-theory in string theory, already require extra temporal dimensions to balance the equations, suggesting that our single timeline might be a fluke or an illusion. But here's where it gets mind-bending. With multiple time dimensions, causality, the bedrock of reality, starts to unravel. Normally, causes always precede effects. But in a two-time world, an event could simultaneously be the cause and effect of another, creating closed loops where history rewrites itself on the fly. Think of a Möbius strip twisted through time. A decision you make today might ripple backward to influence your ancestors' choices, which in turn shape the conditions for your own existence. This isn't just philosophical musing. Physicists have explored how extra time dimensions could allow for a causal phenomena, where particles communicate outside the usual chain of cause and effect, potentially explaining quantum entanglement's spooky action at a distance. Yet there's a catch. Multiple time dimensions introduce instability into the fabric of reality. In most physical models, additional time axes create ghost states, negative probabilities, and energies that shouldn't exist. To reconcile this, some theorists propose that extra time dimensions are compactified, curled up so tightly at the Planck scale that we never notice them, like ants unaware they're crawling on a folded napkin. Others suggest the second time dimension isn't a free-for-all but constrained by hidden symmetries, acting like guardrails that prevent paradoxes from tearing the universe apart. The implications are staggering. If time has hidden dimensions, then free will might not be an illusion, just a higher dimensional phenomenon we experience slice by slice. The future could be a landscape of possibilities, with every choice branching into alternate timelines we're biologically blind to. And if civilizations ever learn to navigate these extratemporal axes, they might unlock technologies beyond our imagination, communication across eras, or even rewriting history without erasing it. Of course, skeptics argue this is mathematical fantasy. After all, we've never observed even a whisper of extra time dimensions, but absence of evidence isn't evidence of absence. Before quantum mechanics, nobody could imagine particles being in two places at once. Before relativity, time's flexibility seemed absurd. The universe has a habit of hiding its wildest truths just beyond the edges of our perception. Whether a profound truth or a dead-end, multidimensional time forces us to confront a humbling possibility. The clock we've been watching all along might be just one face of a cosmic mechanism far stranger than we've dared to dream. What if everything you perceive, every sunrise, every heartbeat, every fleeting moment, isn't the unfolding of an organic universe, but the flawless rendering of an advanced simulation? The simulation argument, popularized by philosopher Nick Bostrom, suggests that our reality might be an artificial construct, meticulously coded by a civilization with computational power beyond our imagination. And if that's true, then time as we know it could be nothing more than a clever illusion, a subroutine in the cosmic program, stitching together discrete frames of existence to create the seamless flow we experience. Think of it like a video game. When you play an open-world adventure, the environment around your character isn't fully rendered all at once. Instead, the game engine calculates only what's immediately visible, saving processing power by ignoring distant mountains or hidden dungeons until you approach them. Your brain works similarly, constructing a stable reality from fragments of sensory input. Now extrapolate that to the universe. If we're in a simulation, the passage of time might just be the system updating its state in discrete steps, Planck-sized ticks of the cosmic CPU, while our consciousness smooths over the gaps, convincing us that time is continuous. This raises eerie questions about free will. In a simulated reality, your choices could be predetermined by the code, with every decision you'll ever make already calculated by the simulation's algorithms. Yet from your perspective, it would feel utterly real, the same way a non-player character in a game might choose dialogue options that were scripted long before launch. Even the apparent randomness of quantum events could be procedural generation, like the unpredictable weather patterns in a virtual world that feel organic to its inhabitants but are fundamentally deterministic under the hood. The implications for physics are profound. Glitches in the simulation, like particles behaving differently when observed, might explain quantum mechanics' strangeness. The speed of light could be the processing limit preventing the simulation from overloading, while black holes act as cosmic garbage collectors, compressing data to free up memory. And if the simulators ever need to pause or rewind their creation, would we even notice? Like characters in a paused game, our entire universe might freeze mid-tick, only to resume without missing a beat. But here's the twist: if time is simulated, it might not flow uniformly for everyone. Advanced users could tweak their local clock speed, experiencing years in what feels like seconds, or stretch moments into eternities, like adjusting a time slider in video editing software. This could explain the bizarre time warps reported near black holes or during near-death experiences. Even déjà vu might be a buffering error where the simulation briefly replays a segment of code. Skeptics argue there's no empirical proof we're in a simulation, but absence of evidence isn't evidence of absence. As we inch closer to creating photorealistic virtual worlds ourselves, the odds that we're the original civilization shrink. And if the simulators wanted to hide their tracks, they'd design the universe with consistent, inscrutable laws exactly like the ones we're struggling to decode. Whether cosmic truth or philosophical thought experiment, the simulation argument forces us to confront time as something far stranger than a river. It might be the universe's most elegant hack, a flickering projection so convincing we've mistaken the render for reality itself. What if the entire universe, every galaxy, every atom, every fleeting thought is hurtling toward an inevitable crescendo, a moment when time itself culminates in a blaze of cosmic awakening? This is the audacious vision of the Omega Point theory, where science and spirituality collide in a singularity of consciousness that transcends space and time. Jesuit priest and paleontologist Teilhard de Chardin first proposed this idea in the early 20th century, envisioning evolution not just as a biological process but as a spiritual journey toward an ultimate point of divine unity. But strip away the theological language and you'll find eerie parallels in cutting-edge physics, suggesting that Teilhard's poetic intuition might have been onto something profound. Picture the universe as a symphony. For billions of years, matter has arranged itself into ever more complex forms, stars forging elements, planets nurturing life, minds weaving ideas. Teilhard saw this as no accident, but a trajectory leading inexorably toward the Omega Point, a final state where all consciousness merges into a transcendent whole, like droplets rejoining the ocean. Modern cosmology adds a startling twist to this vision. If the universe continues expanding indefinitely, as current observations suggest, then entropy will eventually erase all structure, except perhaps for consciousness itself. Futurist Frank Tipler's mathematical reinterpretation of the Omega Point argues that in the far future, advanced civilizations could harness the energy of collapsing galaxies to sustain thought indefinitely, creating a self-sustaining nexus of pure mind. As space-time contracts toward a final singularity, these post-biological intelligences might achieve infinite computational density, effectively becoming omniscient, a cosmic thinking that perceives all of history simultaneously in its final moments. The physics behind this stretches credibility but not logic. Tipler's calculations hinge on closed timelike curves, loops in space-time that allow information to circle back on itself. In the universe's dying breaths, these loops could enable the Omega Point to remember and even resurrect every possible experience that ever occurred, like a flame flickering to life from its own heat. This isn't reincarnation in the mystical sense. It's a brute force replay of quantum states, where every configuration of matter that ever existed is recreated in the singularity's infinite processing power. Your happiest memory, the fall of Rome, the birth of a distant star, all etched eternally into the Omega Point's timeless fabric. Critics dismiss this as speculative metaphysics, and even Tipler admits the theory requires future civilizations to master technologies bordering on magic. But the underlying premise that complexity and consciousness trend toward unity finds echoes in fields from quantum entanglement to thermodynamics. Entropy demands disorder, yet life defies it locally, building pockets of intricate order against the cosmic tide. The Omega Point simply extrapolates this defiance to its ultimate extreme, a universe that escapes heat-death by transforming into something beyond physics altogether. Teilhard might call it God, a physicist might call it a self-aware cosmological constant. Either way, the theory offers something rare, a vision of time that isn't meaningless decay but a journey with purpose. Whether prophecy or pipe dream, the Omega Point forces a reckoning. If time has a destination, not just an end, then every thought we think, every connection we make, might be threads in a tapestry being woven across eternity. The universe may forget itself one day, but in that final, infinite instant, it could remember everything. From Eternalism's frozen block universe to the phantom time hypothesis's missing centuries, from simulation theories' coded reality to the Omega Point's transcendent crescendo, each of these theories doesn't just tweak our understanding of time, it shatters the hourglass and scatters the sand. What makes these ideas so electrifying isn't their strangeness, but how they reveal the flimsiness of our deepest intuitions. We cling to time as if it's the universe's most reliable mechanic, only to discover it might be a street magician, sleight of hand woven into the fabric of existence itself. Consider the audacity of a theory like causal sets, where reality is just dominoes falling in darkness, or the holographic principle, where time emerges from cosmic pixels we can't perceive. Even the most rigorous physics begins to sound like mythology when we peer past the surface. Think about the stories we've inherited: hourglasses, arrows, rivers, all metaphors that paint time as something fluid and singular. But modern cosmology hands us a stranger palette: time as a fractured prism, a knotted rope, a script that writes itself backward and forward simultaneously. The irony is delicious. We invented clocks to measure time, only to learn that time might not even be real enough to measure. Our daily lives are ruled by schedules and deadlines, yet the universe itself might operate without any master clock at all. Here's the beautiful tension at the heart of it all. Every theory we've explored today, from the rigorously mathematical to the wildly speculative, shares one common thread. They all start with the same humble admission: we don't actually know. That admission isn't a weakness, it's the engine of discovery. Whether time is an emergent illusion, a simulation's render rate, or a dimension we're too biologically limited to fully perceive, each idea forces us to kneel before the unknown. And that's where the magic happens. So tell us, which of these visions of time leaves your mind spinning? The poetic circularity of the time loop universe, the chilling precision of the Wheeler-DeWitt equation's timeless cosmos, or perhaps the dizzying freedom of a multiverse where every choice spawns new timelines. Drop your thoughts in the comments below. Debates about the nature of reality are always better with fellow cosmic travelers. And if you're hungry for more mysteries, from quantum riddles to galactic paradoxes, hit that subscribe button. The universe has plenty more illusions to dismantle, and we're just getting started.